In this lecture, we are going to study about quantum mechanics and blackbody radiation. This is lecture 1 of unit 1, quantum mechanics. First, we will see what is the basic difference between classical mechanics and quantum mechanics. Classical mechanics deals with macroscopic particles, whereas quantum mechanics deals with microscopic particles. Can you think of some examples of classical particle and quantum particle? Classical particles are macroscopic particles that are large in size. Like an example is a bus or a car. Whereas microscopic particles examples are an atom or an electron. Next, classical mechanics is based on Newton's laws of motion, whereas quantum mechanics takes into account Heisenberg's uncertainty principle and de Broglie concept of dual nature of matter. You know what are Newton's laws of motion, and also you know what is Heisenberg's uncertainty principle. But what do you understand by this dual nature of matter? Like radiation, matter particles also have got dualistic behavior. That is, they have got particle behavior as well as wave behavior. Thirdly, classical mechanics is based on Maxwell's electromagnetic wave theory, according to which any amount of energy may be emitted or absorbed continuously. Whereas quantum mechanics is based on Planck's quantum theory, according to which only discrete values of energy are emitted or absorbed. We can also see that classical mechanics, the state of a system is defined by specifying all the forces acting on the particles as well as their position and velocities. The future state can then be predicted with certainty, whereas quantum mechanics gives probabilities of finding the particles at various locations in space. So classical mechanics speaks about certainty of results, whereas quantum mechanics speaks about probability of the results. That is the difference between classical mechanics and quantum mechanics. Quantum mechanics comes into picture because of the dualistic nature of matter particles. The next topic that we can see is what is a black body and what is black body radiation. Going by the definition, a body that completely absorbs radiations of all wavelengths incident on it is referred to as a black body. When such a body is heated, it emits radiations called as black body radiations. The other aspects associated with black body radiations are radiations emitted by a body due to temperature is called as thermal radiations. Thermal radiation is electromagnetic in nature and its energy is smoothly distributed over all wavelengths. A thermal source produces continuous spectrum. So speaking of a spectrum, we can see what is the spectrum of a black body after seeing what is the approximation of a black body. You must know that there is no real black body in nature. We can only speak about an ideal black body. Coming to the approximation of a black body, usually we take a sphere as an approximation to a black body. A sphere that is made up of either iron or copper because they are good conductors of heat. And the inside of that sphere is coated with lamp black. The lamp black is the black body. The sphere has got a very narrow opening through which radiations can pass through. As you see on the screen, a cavity made out of a hollow container of any material, preferably iron or copper, with a narrow opening and painted with a lamp black in the inside portion resembles a black body. Now coming to the spectrum of a black body. The spectrum is a graph between wavelength and intensity at different temperatures, steady temperatures. The wavelength is taken along the x-axis and intensity is taken along the y-axis. Now let us say an example. Let us study this phenomenon at say at 3000 Kelvin. What do you observe about the nature of the graph? As you would see, as wavelength increases, the intensity also increases, reaches a peak and then decreases. This pattern or behavior is same for any temperature, be it 6000 Kelvin, 12,000 Kelvin or above it. So each and every steady temperature, what you see is as wavelength increases, the intensity gradually increases, reaches a peak and then decreases. So the spectral distribution of radiation is a function of temperature. Now, do you see any other behavior or pattern in the graph? A careful observation shows that the position of a maximum peak shifts towards lower wavelength with increasing equilibrium temperature. That is, as temperature increases. In the graph, you can see temperature increases means from 3000 to 6000, 6000 to 12,000. As temperature increases, the peaks are obtained at lower values of wavelength. Now, why does this happen? The black body, as we said, the lamp black, consists of atoms. Each atom acts like a oscillator or an atomic oscillator. So they can absorb radiation and give out radiation at different temperatures and different wavelengths. That is why we get such a behavior. Now, to explain this pattern, classical mechanics could not explain the spectrum of a black body radiation because classical mechanics always speaks of a continuous spectrum. Max Planck proposed the Planck's radiation law, which could explain the spectrum of a black body radiation. Therein, in Planck's radiation law, we speak about discrete values of energy rather than continuous spectrum of a black body. Now, just recollecting what we have studied in this lecture, we have basically seen the difference between classical mechanics and quantum mechanics. Classical mechanics deals with macroscopic particles, whereas quantum mechanics deals with microscopic properties of particles. Next, we have seen what is a black body and what is a black body radiation. What is the approximation to a black body and also the nature of the curve that we have obtained. Now, to explain this black body radiation, we have to study Planck's radiation law. So the next topic of discussion in lecture 2 would be what is Planck's radiation law.